What I'm going to do today is I'm going to tell you about some of my research group's work on simulations on blue waters. And in particular, what we're interested in is connecting connecting microscopics to emergent phenomenon. And particularly, we're interested in that in the context of quantum phenomenon. So what we want to do is we want to start with some microscopic quantum model. And then we want to ask, can we understand if there's some interesting, exotic, useful kind of emergent phenomena that comes out of that? And that's what I'll tell you about today. I'll tell you about sort of 3 short vignettes of things that we've really been able to discover that are particularly interesting, but are the kind of things that without the power of blue waters, we really would have had trouble doing. And the slides have a lot of sort of technical details on them. I won't say those technical details while I'm talking. So if you're interested in sort of technical details, feel free to read the slides. Otherwise, just listen and I'll sort of guide you through kind of the interesting and exciting things. So as I said, this is our game. Our game is to start with some simple Hamiltonians that we know how to write down, some microscopic Hamiltonians, and find interesting behavior. So this often goes by the name of things like strongly correlated systems. And this is sort of the obligatory quote to put up from Dirac if you're giving a talk about quantum simulation. But in spite of the fact that it's a little bit overused, I think it's a useful thing still to sort of ground us and say, look, we've known for a long time in the field of computational condensed matter, in my field, that sort of the fundamental laws, the rules are all known. So we have sort of the known laws, and now it's really just a game of taking those known laws and solving them. And what Dirac says is, he says, look, the difficulty lies only in the fact that the application of these laws lead to equations that are too complex to solve. And so what we'll see today is we'll see in what sense massively parallel supercomputers such as blue water is sort of a partial answer to this question. Can we, given 100 years of computational power beyond Dirac, begin at least partially to solve some of these equations that a century ago were in some sense too complex to solve? And what we'll see is that sort of the answer is a partial yes for some questions, and for some models we'll be able to do that. But there's still a lot of things that are outside of our abilities. So unlike simulations in many other fields, there's something fundamentally different about simulating quantum mechanics. We know the rules, but sort of there's a fundamental problem. And that fundamental problem is if you want to simulate quantum mechanics exactly, and in many cases we can avoid that. In many cases we have great approximations that allow us to avoid that. But there are cases where we want to simulate it exactly. And in such cases, the cost is exponential. So you have n things. Maybe these are electrons. Maybe these are spins. Maybe these are something else. But they're quantum things. And the cost to simulate n quantum things will scale exponentially, for example, as 2 to the n. And so that's a rough barrier to climb. And in fact, one of the vignettes that I'll tell you about is a system where we succeeded in doing 48 sites. And that was a big deal. We were very happy that we were able to do 48 sites. It was the minimum number of sites that we would need to discover sort of this interesting thing that I'll tell you about. And now, after 50 years of sort of Moore's law, we can now do 50 sites. So there are lots of reasons why this exponential exists. There's lots of stories you can tell. In some cases, it takes an exponential number of numbers to store the state. In other cases, you're stochastically sampling the state, but there's a sign problem. In other cases, you can represent the state in other ways, like tensor networks, but the bond dimensions grows exponentially. OK, so as I said, I'll tell you 3 vignettes. These are the collaborators on these different vignettes: spin liquids, many-body localization, and superconducting materials. I want to particularly highlight sort of the postdocs and graduate students sort of at the front of this list who's really done a lot of the work. They are, as I said, responsible for much of the work in this talk. So my first vignette is to tell you about spin liquids. Spin liquids are probably certainly the most kind of exotic and thing that I know about in condensed matter physics. And finding a microscopic Hamiltonian that gives you a spin liquid is a big deal. I can probably count on my fingers the number of microscopic Hamiltonians that we know about where we have good evidence that they give spin liquids. And so let me tell you 2 or 3 things about why spin liquids are so cool. To begin with, they're topological. If I take a boring phase, if I take a magnet and I paint it on a sphere, or I paint it on a donut, or I paint it on a Klein bottle, it really doesn't care. I don't care what I paint my magnet on. A magnet more or less acts the same. But nonetheless, a spin liquid, this exotic phase that I'm telling you about, knows what kind of topology I painted on. If I paint it on a sphere or I paint it on a donut, it acts differently. In particular, it has 1 ground state on a sphere and 2 ground states on a donut. And so that's pretty neat. Another thing that's nice about spin liquids is that they're extremely entangled. Many of you know that entanglement is somehow the heart of quantum mechanics. And spin liquids are amongst the most entangled sort of ground states that you can get. In particular, what do I mean by that? We can quantify it. We can say start with something not entangled and build me a spin liquid. And we can show, the community can show that to build such a spin liquid requires a long quantum circuit. And the final thing that's exciting is spin liquids and things like it have potential to be useful. In particular, spin liquids have the potential to support something called anyons. So we're all used to sort of fermions and bosons. A fermion, I take 2 spins, 2 fermions, electrons, I swap them and I pick up a minus sign. An anyon kind of works like that, but I don't pick up a minus sign. I might pick up a phase, or even more exotically, I might pick up some unitary transformation. If we had these and we had the right type of anyons, we could build a topological quantum computer. If you want to build a quantum computer, you want to build a topological one if you can, because there the hardware is robust, and you don't have a factor of 1,000 doing software error correction. So the whole name of the game is, can we take microscopic Hamiltonians and can we find spin liquids? And I'll tell you about one today. Unfortunately, it's not the most exotic one. It's not the most useful for building a quantum computer. It is nonetheless a new microscopic Hamiltonian that gives a spin liquid. So here's the Hamiltonian for experts in the room. It's a spin system, an XXZ Hamiltonian, and some under a magnetic field. And so what should you do if you're given such a Hamiltonian? Well, really, you should go ahead and you should try to solve it exactly in the biggest systems you can. And in this case, the biggest systems we can is 48 sites. And it turns out 48 is a magic number for this system because it's a cluster with the right symmetry that allows us to calculate all the things we need to calculate. So here's the game. You stick it on a donut, and you look at the energy as a function of some perturbation, and you find 2 states, those 2 states right there, that are essentially degenerate. These are the 2 states that I told you about that you painted on a donut, and it becomes 2 degenerate ground states. And then what you do is you say, look, what I'm going to do is I'm going to twist the boundaries. So typically when you do a simulation, if you walk off the right, you come back on the left. Here we're going to do something different. We're going to walk off the right, and when we come back on the left, we're going to pick up a phase. And so you twist the boundaries in all ways, and you look at the energy as a function of the twisted boundaries, and you see that the degenerate states are gapped out from anything else. Now to do that requires an insane amount of computation, but once you've done that, you've given yourself a candidate for having such a spin liquid. Once you have such a candidate, there are 2 smoking guns. There's a computation of something called the Chern number. This is the Berry phase over those twists. It's not important that you know what that means. You just calculate some topological property of the system. The other thing you do is you calculate something called the modular S matrix. This tells you the type of anyon you have. Again, it's not important that you understand what that means particularly, but you cut your system into 2 pieces, and you find sort of the minimally entangled decomposition over those 2 pieces. OK, those are all details. The point is we've done those 2 things. And for the Hamiltonian that I just showed you, it has a Chern number of 1/2, and it has the right analytically predicted modular matrix. That means it's a new chiral spin liquid. So given the power of blue waters, we've sort of added to this very short list of spin liquids that are known. We've got strong numerical evidence of it. Just to say a few quick words about sort of what this takes on blue waters. So essentially, for even the first plot that I showed you, to get this gapped out state, you need to do about 400 twists. Each of those twists require about 30 blocks. We're doing some sort of exact diagonalization. And each of those blocks requires kind of on the order of 150 node hours. So this is sort of an insane calculation in terms of sort of core hours to pull off. This is how our exact diagonalization code scales. This is the newest version of the code. So some of this data I showed you is run on a slightly worse version. But we scale nicely out to sort of 50 to 100 nodes. So one of these sort of blocks can be done in a couple hours. And so if we wanted, we could do this entire calculation. The rest of it is embarrassingly parallel in 3 or 4 hours. We're not usually that brave. We usually like to do a little bit and then check and do sanity checks and things. But that's the kind of calculation that we can do there. OK, that's my first vignette. Let me tell you my second vignette. Let me tell you about another really cool phenomenon in physics called many-body localization. This is something that's really sort of exploded in interest in the last couple of years. So StatMech 101, if I start with some coffee cup sitting in my room and I let it cool, StatMech 101 tells me that coffee cup will eventually cool to the temperature of the room. That's how statistical mechanics works. Now, it turns out that almost all systems obey statistical mechanics. That's why it's StatMech 101. But it turns out that if you take a system that has some disorder in it and some interactions, you can come up with something that doesn't thermalize, where a chunk of the system doesn't act as a heat bath for the rest of the system. And that's really strange. That's really saying I stick my coffee cup down there, and it stays hot forever. And so there's a lot of work trying to understand this. And it turns out that the sort of linear algebra of understanding this is the following. What you want to do is you want to take some spectrum, and you want to pull out an eigenstate in the middle of that spectrum. But this spectrum has something like, if you do 2 to the 20 sites, 2 to the 20 states in it. Or it has 2 to the 100 states in it. And so the density here is something like 10 to the minus 30. So you're trying to resolve one state whose nearest states to it are 10 to the minus 30 away. And that's sort of the technical challenge. So when it's only 10 to the minus 5 away, when we have 20 sites, we can do things like shift and invert. When it's 10 to the minus 30 away, that's really below machine precision, and we've had to develop new numerical algorithms to run on blue waters. So I should say, because this is a disordered problem, you need hundreds and thousands of samples to study it. So this is sort of the linear algebra challenge, the thing that we've had to do. Let me just tell you some of the physics that we found. One of the things we've discovered is that there's some universality in the critical region. So this is a totally different type of phase, a totally different type of phase transition. And so whenever a physicist sees a phase, they'd like to know, is there something universal about it? Universality is sort of like crack for physicists. And so what we're able to show doing simulations on, say, 16 sites, 20 sites, et cetera, we're able to show that all sorts of different systems fall on this universal set of curves. And I'm not going to explain the curves. That's not really important. What's important is that we were able to kind of see this universality. As I said, to go beyond 20 sites, to go to 100 sites, we really had to invent a new algorithm. So we've invented a new type of DMRG. This is a common technique in physics. And what does our modified DMRG do? Our modified DMRG sweeps back and forth among all 100 sites. For each site, it produces some effective Hamiltonian. And then it picks an eigenstate of that effective Hamiltonian at a given energy. Again, the details aren't important. What's important is that the power of blue waters really allowed us to test this algorithm out and sort of go through lots of iterations of possible algorithms quickly so that we could succeed in discovering and sort of converging to an algorithm that's sort of most efficient, that's really sort of opened up the ability to study this new many-body localized phase with numerical methods in a way that before we had this was sort of not possible. OK, and then we could do physics with it. The algorithm we can show works reasonably well. And so we can ask questions like, well, how does the entanglement scale? You'll notice lots of projects here involve entanglement. And what we find is when the disorder is strong, when we're in the many-body localized phase, the entanglement has very little dependence on system size, which is to say that the entanglement there is very special. And once we walk out of the many-body localized phase, the entanglement explodes. There's a huge dependence on system size. So that's nice. We can also see that our coffee cup refuses to cool down. In particular, what we can do is we can look at something called the eigenstate thermalization hypothesis. So this is sort of a formal metric to decide whether or not your system thermalizes. If your system thermalizes, what you should see is that as you tune energy, local properties stay the same. If I look at a little chunk of my system as I tune energy, the system from energy to energy should be more or less constant. And so this isn't a normal, boring, ergodic phase. That's exactly what happens. I tune the energy, and my property doesn't change very much. Now that we can go to very big systems, now that we can go to site 30 sites, 100 sites, et cetera, we're able to look at this in the many-body localized phase. As we tune the energy, what you see is that the properties, the local properties, are scattered all over the place. OK, so I'm not going to tell you why this means your coffee cup doesn't cool down, but that's the implication. The implication is that if I step a little bit in energy, if I'm sitting at that energy, and it depends whether I'm at state 1 or state 1 plus 10 to the minus 30, that means that there's no equilibration. And that should seem very plausible to you. If very, very small perturbations change my properties in some huge amount, it shouldn't surprise you very much that my system doesn't thermalize. OK, so that's my second vignette. Can I just ask how much time I have left for?
5 minutes.
Great. OK, good. So now I'd like to sort of talk about my third vignette. And here I'd like to talk about superconducting materials. So this is sort of a rough phase diagram of the cuprates and of a set of materials that superconduct. And you'll see lots of phases. In particular, you'll see the superconducting phase. Not surprising, it's a superconducting material. You'll also see there are other phases. There are these pseudogap and strange metal phases. And the pseudogap and strange metal phases are probably the most poorly understood phases in superconducting materials. So superconductivity has been studied for a very long time, and there's still lots we don't understand about all aspects of it. But there's a reasonable argument to be made that almost nothing is understood about the pseudogap and strange metal. And one of the major, maybe key stumbling blocks to understand it is we don't have any microscopic models that give us a strange metal or a pseudogap. And so what we'd like to talk about here is a simulation that we were able to do on Blue Waters that allowed us to write down a microscopic model and show that gives a strange metal. In fact, as I said, superconductivity is also not very well understood, but at least the broad mechanisms that are understood. You have some electrons, somehow or other they pair together in bosons. Bosons like to condense and superconduct, or become superfluid. That's what bosons do at low temperature. If you have a bunch of bosons, either they insulate, they form some sort of solid, or they like to superconduct. And in some sense, the key to understanding these pseudogap and strange metals is there's good reason to believe that they are paired electrons. ARPES experiments and others show that the electrons pair together, but they seem not to condense. And this is a very strange thing for bosons not to do. Bosons, sort of their natural state is they want to condense. This is an AMO experiment that people do. You just get a bunch of bosons together, you cool them down, they condense. And so in some sense, we're after non-condensed, non-solid bosons. And as I said, there's good reason to think that this is sort of a key stumbling block to understanding superconductivity more globally. So here's our model. Our model is the following. We have a Hamiltonian, and this is a microscopic Hamiltonian. And there are a bunch of electrons. They live in a square lattice. And there's only one electron per site, and there's a ring exchange term. So that's described here. I have one spin up and one spin down, and they can exchange like this. OK, that's the model we have chosen to write down. And what we're going to do is we're going to simulate this using quantum Monte Carlo. So typically, quantum Monte Carlo has a sign problem if you're doing fermions. It turns out that we can show that in this very special model, there exists a unitary transformation that removes the sign problem. So it's still going to take us 500,000 node hours to do this simulation, but at least it only takes us 500,000 node hours and not much more than that. So what are we doing? We're doing diffusion Monte Carlo or projector quantum Monte Carlo. So let me give you the 30-second introduction to diffusion Monte Carlo. It's essentially a stochastic imaginary time evolution. So if you imagine that these are snapshots in imaginary time, you start at the beginning here at time 0. At time 0, you sample a bunch of configurations from this wave function psi trial. And so this is, I don't know, we use about 1 million samples sampled from what is a possible 2 to the 228 states. So it's an extremely sparse sampling, but it's some sparse sampling of this space. And then what you do is you stochastically evolve those samples. So you apply e to the minus tau h to that set of samples. You essentially do one imaginary time step, one stochastic evolution, and you do this over and over again. In practice, for the systems we're doing, we need about 1 million samples. We have to do about 8,000 time steps for this to converge. And then this is a technical detail, but there are a couple experts in the room. We have to do forward walking to get anything reasonable, and we have to do pretty bad forward walking about beta 5 or 6. So this is how quantum Monte Carlo works. And then at the 8,000th time step, you can look at your stochastic sample. And when you look at your stochastic sample, you can measure properties of it. And those properties will be properties of your simulation after this technical detail of forward walking. OK, and so now we can ask ourselves, what property should we look at to decide if we have something interesting? And so a good answer to that question is we should look at the structure factor. So the structure factor is shown here. This is kx, ky. This is the amplitude of the structure factor. And this is exactly at half filling. At half filling, nothing interesting is going on. There are peaks in the structure factor, these peaks that I've circled here. Those peaks indicate that we have a charge density wave. We essentially have a crystal. There's nothing particularly exciting about that. One can extrapolate and show that, in fact, nothing exciting goes on. OK, so that's the boring piece. We can also go to very low doping. Again, we can look at the structure factor. Here we see peaks, but very small peaks. They're about 0.8. We can look at the charge-charge correlation function. When we look at the charge-charge correlation function, there are essentially stripes. So that's appealing and a little bit tantalizing. We know that stripes are believed to play roles in superconducting materials. And so maybe this has something to do with the stripes present in superconducting materials, although that's not obvious. And so this is really sort of another talk. But there is something interesting going on at very low doping, when you have very few electrons in your system. Sort of the really exciting thing, the thing that we were very happy about, is that at intermediate doping, you find something really exciting. So this is the plot that is sort of the magic plot. So what is this showing us? So this is the structure factor of our system at slightly less than half doping. And the key thing that you see if you stare at it for a little bit is, one, there are no peaks. But two, the key thing is that there's this X structure. So at kx equals 0 and ky equals 0, there are these gapless lines. OK, so that tells you a couple things. One is that this is the sort of known signature, sort of the smoking gun of a theoretical phase called the exciton-Bose liquid. So that would be a bunch of fermions pairing into bosons that don't condense. In addition, you can ask yourself, does it conduct? We want a strange metal, right? We don't want a strange insulator. And so what you can do is you can look at the structure factor as k goes to 0, as q goes to 0. And you can see if it's linear or quadratic. And what we're able to show is we're able to show that it's linear. And if it's linear, what that tells you is that tells you that the system conducts. So this is really sort of a great success. What we've done is we have a microscopic model, and we have extremely strong numerical evidence that this microscopic model generates, well, at least a strange metal. We're not sure it's the strange metal that shows up in superconductivity. That has other kind of translational symmetry breaking that we're not necessarily capturing here. But it's the first time I know of where we have sort of a bulk 2D microscopic model that we can solve numerically that gives a strange metal. And so that's really nice. OK, so this is the phase diagram of that system. We've written down this Hamiltonian, which is this microscopic model with ring exchange. At exactly half filling, we have the charge density wave, kind of boring, but reasonable that it's there. At low and high filling, we have phase separation or this stripy behavior. As I said, potentially interesting, but kind of another study and another talk. But in the middle, we have really this strange metal. We have this exciton-Bose liquid state. And so we have this microscopic model that now we can probe to try to understand properties of strange metal. There's also another story to be told about what's going on in the spin degrees of freedom. These fermions have spins. I will not tell that story today. So in summary, where are we? What I've told you is I've told you sort of 3 short vignettes about really sort of interesting, exotic, emergent phenomenon that has come out of simulating these microscopic quantum Hamiltonians, phenomenon that really we needed sort of the scale and the power of blue waters to be able to get to. I told you about this chiral spin liquids, where we were able to sort of find a new microscopic Hamiltonian that gives a spin liquid. I've told you that we've been able to understand universality as well as other entanglement properties of many-body localization, and that we have what is sort of the first 2D bulk example of a strange metal coming from a microscopic Hamiltonian. This is just sort of a scaling plot sort of some stuff we're doing in the future. We're beginning to use sort of extremely powerful, systematically improvable variational ansatz to also look at other properties of superconductivity. And OK, you can't read anything on this, but this is Blue Waters nodes versus scaling. And our scaling is linear out again out to about 1,000 nodes.